Hello everyone, and welcome to AWS Databases video series. Here, we talk about AWS Cloud Databases, their features and functionalities, and we also see how you can use these features to solve some common database issues like performance, availability, scalability, and more. My name is Aditya Samant. I'm a Senior Solutions Architect here at AWS, and I specialize in database technologies, including Amazon Aurora and Amazon RDS. Last time we discussed Amazon Aurora Global Databases. Today we're going to continue that discussion and we are going to talk about Managed Planned Failover feature. We're going to see how this feature helps you with the issues of cross-region disaster recovery and data locality that come with a global scale. So let's dive in. Okay, so for agenda, today we will do quick overview of Amazon Aurora architecture. Then we will do a quick overview of the global database architecture. Then we'll look at some of the use cases for managed planned failover and how it works. And then we'll do the demo. So Amazon Aurora is a database that we built for the cloud. It takes advantage of the abundance of storage and compute that is available in the cloud, which makes it highly scalable. One architectural uniqueness about Aurora is that we decouple the compute from storage, which enables these two components to scale independently. At the bottom of the slide, you can see the distributed storage subsystem that Aurora uses, which stripes the data across potentially hundreds of storage nodes. We replicate the data across multiple availability zones while simultaneously backing it up to S3, which is our object storage subsystem. This makes the storage highly durable and resilient to failures. The Aurora storage subsystem can grow and shrink automatically as the database grows and shrinks. Amazon Aurora can have a single primary node, which is a read/write node, and up to 15 read replicas. We can also define auto-scaling policies that can spin up and spin down read replicas based on the workload. The primary node can scale up and down in provision mode, and when you make sizing changes on the primary node, that usually requires a restart. But we also have a serverless Aurora mode, which can scale up and down automatically as the workload demand grows and shrinks. At reInvent 2020, we also discussed plans to release serverless v2, which makes the scaling even more seamless. So overall, the Aurora architecture is designed to be highly available, highly resilient to failures, and scalable and elastic. So let's quickly talk about some of the use cases for Aurora Global Databases. Aurora Global Database is designed for globally distributed applications, and it allows a single database to span multiple AWS regions. The use cases there are two primary use cases, right? So the first use case is fast cross-region disaster recovery. So if you have an application that needs to be available in case of a regional outage, that can happen due to, let's say, network issue or several other things, Global Database can help. Global databases use physical replication technology to keep the database in sync across regions. And if there is a need for failover, it can be done very quickly, usually in single-digit minutes. One thing to keep in mind here that the cross-region replication is still asynchronous, which means that there is a possibility of some data loss when you do a failover. Another use case is data locality. If you have an application that is globally used, you can use the global database to make data available close to that local region. When the application needs to read from the database, it can read from that region directly, making the results return pretty quickly. This makes user experience in that region really, really good. The same asynchronous replication still applies here, so there will be some lag, usually under a second. So as long as your application in the secondary region can tolerate replication lag, you should be fine. Let's do a quick overview of how global database works. Like I mentioned in the slide before, we use physical replication across regions. You can see that we have our primary region, which has an outbound replication fleet, which receives all the delta changes from that region and sends it to the secondary region. The secondary region In the secondary region, we also have an inbound replication fleet, which receives those changes and passes it to the database storage, which gets applied directly on the storage nodes. Since we're using physical replication, the replication lag on secondary is typically less than a second. Since we're continuously applying the changes to the secondary, in case of a failover, promotion of secondary happens in under a minute as well. Now, this of course is just a quick overview. If you'd like to get a deep dive, I highly recommend that you go take a look at our global databases deep dive video, for which I'll leave a link in the description. So now let's talk about the managed failover feature. This feature was released in early 2021, and it supports both MySQL and PostgreSQL versions of Aurora. So what is the use case here? So one use case is if you want to set up and easily test cross-region disaster recovery. Managed plan failover will help you do just that in a completely automated fashion. When you're ready to do the failover or a failover drill, you just cause a failover from the console or from CLI, and the cluster will automatically failover to the other region. Another use case is when you have an application that needs to move from one region to the other region. Again, you click a button on the console or run a CLI command, and the cluster moves over and switches roles between the primary and secondary. You can do this failover with 0 RPO, as in no data loss. And we'll see how this is done in the next slide. This is actually quite a big improvement over our, when this feature didn't exist, right? So when this feature didn't exist, the failover meant you had to actually break the global cluster topology. This would make the secondary region a standalone cluster, and then you would use it as a DR or to make any writes. So now you don't have to do any of that. It is completely automated. When you do a failover, the topology doesn't break at all. So in summary, managed plan failover reverses the replication direction, promotes the secondary to be the new primary without losing any data or breaking the global database topology. So and it's done in a completely hands-off way. So that's pretty cool. All right, so let's look at how the managed plan or plan managed failover works. So on this slide, we have our primary region, which is the Ohio region. As you can see in the primary region, we have our primary node and 2 read replicas. They're connected to the distributed storage subsystem. This storage subsystem is getting replicated to 2 secondary regions, Northern Virginia and Ireland. And then the app connects to the primary node. So let's say that we click to promote North Virginia, which is the current secondary region, to the primary region now. What we do is we stop the writes in the current primary region, which is the Ohio region, right? So we drain that node, make sure all the writes are stopped. Now, the other thing we do is we also wait for all the secondary regions to completely catch up, right? So the writes on the primary have stopped, and then now we are waiting for the secondary region to catch up. So if you remember in the last slide, I said that, hey, when you do a plan managed failover, there is going to be 0 RPO. And this is how we make sure that there is 0 RPO, because we're letting the secondary regions catch up to that replication. Now, once the replication catches up, we promote the North Virginia region to the new primary, and then we also reestablish the replication. So we reverse the replication direction from Virginia to Ohio, and also to any other secondary regions from the new primary. And now the new writes are available in the new primary, which is North Virginia region. And at this point, you simply redirect your application to the new primary, and you're good to go. So pretty simple and straightforward. All right, so that was kind of the theory behind planned managed failover. Let's take a look at the demo and see how this works. Okay, so the first thing we're going to do as part of this demo is we will examine the global cluster topology. Now, we will not be creating a new global cluster as part of this demo. If you'd like to see how to create the global cluster, I highly recommend you look at our global database deep dive video. I'll leave a link in the description. So on the top here, we have our global database cluster, which is the container for the entire global databases, which contains both the regions. So the name of the global database cluster is global-cluster. Next, we have our primary region, which is global-region-1. And as you can see, this is US East 1. And in this region, we have reader and writer both. Now, if we look at our connectivity and security, you would see that we have two endpoints. There is a cluster endpoint, which is also the writer endpoint. And we have a reader endpoint. And you can see that both of these endpoints are available. So now if we switch to our secondary region, let me switch to the secondary region tab. You would see that our secondary region is called global-region-2, and it is in US West 1, and it has only a single reader instance. Now, if we go down here and look at the connectivity and security, you would see that this also has two endpoints. It has a writer endpoint and a reader endpoint, but you would see that the writer endpoint is actually inactive. So when we do the failover later in the demo, you would see that this inactive writer endpoint would become available and we would be able to connect to it. So before we do anything else, let's go ahead and connect to these regional endpoints in the global database cluster and see how they behave. So I have two Linux clients here. The client on the left-hand side is in US East 1, which is the current primary region. And the client on the right-hand side is in US West 1, which is currently the secondary region. So what we'll do is we will connect to the primary writer endpoint from US East 1, which is also the primary region. Okay, so if you notice here, the endpoint I'm using is the global region 1 cluster endpoint, which is the writer endpoint. And I'm going to go ahead and connect to it. And as you can see, it works fine and I'm able to connect. Now, the next thing we're going to do is we're going to go to the secondary region and we will try to connect to that writer endpoint on the secondary and see if it works. So if I try that, you would see that we get an error and says that it can't find this host. The reason why it can't find the host is because this writer endpoint or the cluster endpoint on the secondary region is currently inactive. So the only way we can connect to the secondary instance is by connecting to the reader endpoint. So let's do that. Now, if you notice here, now I'm connecting to the reader endpoint, and you would see that this -RO in the reader endpoint name here. Okay, so I'm able to connect now. So let's go ahead and create a table on the primary region, and let's see what behavior we get. Okay, so I'm just going to create a quick table. We're going to keep this super simple. We're not going to do any fancy querying here. We just want to observe the results of creating a table, inserting some rows, and see how that behaves on the global database. So let's go ahead and create a simple table. This table only has an integer value, and it also captures when that value was inserted, right? Super simple. Now I'm going to go ahead and insert a row into that. Okay. Now the next thing we're going to do is let's do a select and make sure that the row was inserted. So we see that the row was inserted at this time. Now we'll run the same query on the secondary. And you see that one row was added and it got replicated immediately. So let's just quickly add another row here and immediately run a select here. And you see that on the secondary region, the inserts are getting very quickly replicated. And we have seen that the replication lag is most of the time under 1 second, even if you create clusters between US East and US West, which is between coast to coast. So the next thing we're going to do is we are going to cause a failover. Okay, so let's head back to our console and click on the global cluster identifier. We're going to go ahead and click on actions, and then we're going to click on failover global database. Right? It is that simple for doing a failover. Now, the option we are presented is which region we need to failover to. So keep in mind our global region 1, which is in US East 1, is our primary. So the only other region we have added is global region 2, hence that is the only option presented to us. If we had more than one region, we would have the ability to failover to one of the other secondary regions. So you can see currently the cluster is all caught up, so there is no lag, and it also shows us the status and number of instances, which is just a single instance right now in the secondary region. So let's go ahead and click on that and click on failover global databases. And this would kick off the activity of failing over, right? So you can see that the status is shown up here on the top. And if you remember from our presentation, this goes through the 4 steps of failover. You can also see the same status on the global cluster. It shows that it's failing over. And it's going to go through all these 4 steps, and we're going to observe them as they move between those statuses. Okay, so now you can see that our primary region has gone from available to modifying, and the role now shows as pending for both regions because we will end up reversing the roles. So this is the primary region has now stopped accepting any writes, and it's waiting for the secondary region to catch up the replication. Okay, so now we are in our second step of our failover. You would see that it's saying that the cluster global region 1 is being demoted to secondary, and we also see that it's being reflected in the status. If you also notice, the order of regions have flipped. So now global region 1 is at the bottom and global region 2 is at the top because the global region 2 will become primary, even though it still shows as role as pending. And in the short time we were speaking here, all the 4 steps have been completed. The status still shows as failing over, so we'll give it a few more seconds for this to complete. Okay, and now you can see that the failover has completed, and our roles of these 2 regions have changed. Our second global region 2 is now the primary role, and global region 1 is now secondary. Now the status still shows modifying, but let's hit a quick refresh on the browser and we should see that the status for the entire cluster is available. And there we go. So in summary, we were able to do the entire failover right here from the console. We simply clicked on a button. We reversed the order of replication. Our global region 2, which is in US West 1, now became the primary, as you can see here. And the global region 1, which is in US East 1, became the secondary. So now let's do a quick experiment and try to connect to these new primaries and secondaries using our queries as we did before and see how that works. Okay, so now that the failover has completed, let's try to execute the same connection again and see what happens. So I'm going to run the same exact connection as we tried to do before from the US East 1 region. Now the US East 1 region is a secondary, right? So let's try to connect. Now this is the same connection string, the same endpoint as we did before, and it fails. Now the reason it fails is because after the failover, this endpoint has become inactive. So if we look at the global region 1 under connectivity and security, our old router endpoint has now become inactive. So we can't connect to it anymore. So the only way we can connect to it is by going to the reader endpoint. So let's do that again. If I connect to this endpoint, you see that there is global region 1-RO in the name. We can connect to it without any problems. Now let's connect to the US East 1 region, but this time we will connect to the writer endpoint. See, there's no -RO in this name, and we connect just fine. Now we will just redo our query of inserting a value. Now instead of running from US East 1, I'll run the insert from US West 1. And we will do the select from US East 1, which is the secondary region now. And we see that value here as well. So essentially what we have done here is we caused a failover from the console, and we used the new connection strings to connect from both regions, and we were able to see the effects of failover and how the direction of replication reversed, and also we saw how the new endpoints became kind of swapped their modes. So this is great, but one of the common things that customers ask us is, how do I manage connection strings? So I'm going to show you a quick improvement over this architecture that you can do using Route53, and how you can connect using the same endpoint even when failover happens. So let's look at how you can use Route53 DNS service to manage your global database endpoints so that your applications don't have to change their connection strings after a failover. In this architecture, we're using Route53, and we have created a private hosted zone. The private hosted zone lets you add VPCs from both regions and lets you direct your incoming request to the active writer endpoint. So in this state, we have our primary region, US East 1, on the left-hand side, and the secondary region, US West 2, on the right-hand side. We have created a private hosted zone that can reach to both regions and the respective VPCs where the global database cluster resides. And we create a CNAME record that points to the current writer endpoint in the primary region. After the failover, we simply update the CNAME record to the new writer in the secondary region, and applications will never have to make any connection string changes and will continue to talk to the same Route53 DNS endpoint. You can make this architecture completely hands-off by creating a Lambda function that makes this change automatically without any sort of manual intervention. Thank you so much for spending the time here with us today going through this video. I hope you learned a little more about managed planned failover feature of Amazon Aurora global databases. I hope you enjoyed the demos. If you have any questions, feel free to reach out to your AWS teams. As always, here's wishing you happy cloud computing from everyone here at AWS. Thank you so much.